Let us now get back to algebraic differentiation. We have seen that this is quite tedious work since we have to use this differential quotient, this limit for delta x going towards 0 of f of x plus delta x minus f of x divided by delta x, somehow trying to find this limit. Luckily, this is not necessary in the normal case because there are certain new rules that we can apply and that simplify our life a lot. So let us have a look. The first rule is if f of x is just a constant function, then f dash of x, the derivative, is just 0. Second rule, if I can write f of x, or if f of x is just x to the power of n, so a power function, then the derivative is n times x to the power of n minus 1. So I have x to the power of n. I'm looking for the derivative. I just take the n in front here. I put it here, n times. And then I copy this just using an exponent for the exponent instead of n minus 1. That's it. Third rule, if I have a function f of x that is c times another function, so a constant times another function, so the result is very intuitive, just a constant times the derivative of the other function. And if a function is the sum of two functions, then the derivative of the function f is just the sum of the two derivatives. This means I can just take each function by itself. I look at u of x, I take the derivative, I look at v of x, I take the derivative, and I add the two. Here also c times u of x, so I sort of can ignore the c. I just have to take the derivative of this u of x. Once I found that one, the u dash of x, I just add again the c times in front. We will see that this does not apply in more complex situations. But here, for these simple types of operations, this holds. So these are these rules. They have, by the way, some names. So constant rule, that the derivative of a constant is 0. Power rule, x to the power of n, the derivative is n times x to the power of n minus 1. Scalar multiple rule, we call that. That is that I can just multiply with the constant, that I keep that in front, and the addition rule that I can take there is an addition, I can take the two derivatives separately. Let us look at some examples that it becomes clearer. So if f of x is x to the power of 7, x to the power of 7, that's this case here. So I need rule 2, and I get this means the n is 7, so I get 7 times x to the power of 7 minus 1, so 7 times x to the power of 6. Example 2, f of x is 3 times x to the power of 5. Let's take it apart very formally. So f of x is just 3 times some function of x, u of x, where u of x in this case is just the x to the power of 5. And now, here using rule 3, we get f dash of x is just 3 times u dash of x. Here we want to find u dash of x, the derivative, so we can apply rule 2, this one here, and we get directly 5 times x to the power of 4, and now put that all together again, and we get f dash of x is 3 times 5 times x to the power of 4, so 15x to the power of 4. In future, we will not do this complicated taking it apart, but we'll just say, okay, the derivative of that is just 3 times the derivative of this here. This is, so we get 3 times, then the derivative of this here is 5 times x to the power of 4, so we can write that in one go. but for the moment this is fine just to understand the rules. Think a moment about how to solve example 3, which rules to apply. And here comes the solution. So we can write f of x as the sum of two functions, u of x plus v of x, where u of x is the 2x to the power of 5, v of x is the x to the power of 3. Now, according to rule 4, the f dash of x is u dash of x plus v dash of x. And here we can apply now rules 3 and rule 3 and rule 2, as we did in example 2, and we get u dash of x, taking the derivative of this here, is first 2 times, that stays, and then x to the power of 5, the derivative is 5 times x to the power of 4, and here that's just the rule 2 that we need to apply, so we get v dash of x is 3 times x squared. And now taking that all together, we find f dash of x is just 10x to the power of 4 plus 3x squared. And again, like I said before, when we do that regularly, we will not take it formally apart so complicatedly, but we'll just do it directly, saying, well, I have to take this derivative. I get this one, so 10x to the power of 4 plus this derivative, which is 3x squared. Example 4, think about how we can rewrite this expression that we can apply immediately one of the rules above. Well, here comes the solution. The third root of x is x to the power of 1/3. And this means we can apply the rule 2, and we get f dash of x is 1/3 times x to the power of 1/3 minus 1. So 1/3 times x to the power of minus 2/3, which is the same as, now if you want to do it further, it's 1 divided by 3 times x to the power of 2/3, which is the same like 1 divided by 3 times the third root of x squared. Whatever we do here, let's say we call this our final solution. In the end, that was just the algebraic transformation. The actual derivation, differentiation was done here. What can we do in example 5? What do we have to do with this function that we can apply the upper rules immediately? Well, the idea is just expand the expression. We get 9x squared plus 6x plus 1. And now, when we want to find the derivative, we have just to apply the rule 4, which means we're summing these. We have a sum of different functions, and then we apply rule 2 and rule 1. So, what are we doing actually? First, it means we can take the derivative separately for each of these. So 9x squared, well, 9x squared is 9 times 2 times x to the power of 1. Then the next one, 6x, is 6 times 1. The x is 1 to the x is x to the power of 1 times x to the power of 0, which means it disappears. And the derivative of 1, this is a constant, so the derivative hereof is 0. So our result is just 18x plus 6. Now try example 6 on your own. Well, what do we have to do? First, we have to do something with this here. Important, you can't, there is a multiplication here, so you can't just say, I'll take the derivative of this times the derivative of this. There is no such rule. We have a multiplication, so that does not apply. What we have to do instead is we have to expand here. So we get x to the power of 7 plus 4x to the power of 5. And now we can take that apart. Well, f dash of x is 7x to the power of 6 plus 4 times 5 times x to the power of 4. So we get 7x to the power of 6 plus 20x to the power of 4. Just to show you, if you did it wrongly, what might happen? Wrong. I could think I'll do just with the multiplication the same. So I'll take x to the power of 4 is 4x to the power of 3 times the bracket. Bracket would be derivative of the bracket 3x squared plus 4x. The derivative of 4x is just 4. And we would get 12x to the power of 5 plus 16x to the power of 3. And as I said, this is wrong. Now you can try example 7. Again, you will have to transform it somehow. So here comes the result. We take that apart as two fractions. And then we get here 2x to the power of 4. And since we cannot work with minus 3 divided by x, we have minus 3 times, and now we have 1 divided by x, and 1 divided by x is just x to the power of minus 1. And now we can just apply the rules, and we get f dash of x is, using the addition rule, we can take this derivative first, and the 2 stays here. Then x to the power of 4, using the rule 2, we get the derivative 4 times x to the power of 3, minus, again using this constant, scalar constant multiple rule, we can keep the 3 here in front, times, and now we use the rule 2, and rule 2 says I have to reuse here times n, the n here, so times minus 1 times x to the power of minus 1 minus 1. So the result is 8x to the power of 3. Minus 3 times minus 1 is plus 3. So I get plus 3 times x to the power of minus 2. And rewriting a little bit nicer, it's 8x to the power of 3 plus 3 divided by x squared. Just to be clear, the actual differentiation of the function f is here. The rest is just algebraic transformation. Let us note the following. First, the rule 1 is a special case of the rule 2. The rule 1 just says if f of x is c, then the derivative is 0, if the f of x is a constant. Well, I can say f of x equals c, it's the same like c times x to the power of 0. You remember something to the power of 0 is 1. And now I can apply the rule 3 and rule 2 when I take the derivative. The rule 3 just says, well, it's c times, and then x to the power of 0. I have to take the rule 2, so I have to take the to the power of n, the n in front. I get 0 times x to the power of 0 minus 1. Minus 1, I'll write it like that. And we see this whole thing is just 0. A second thing, more important, if I have a function f of x that is just c times x, so some constant, well, so f dash of x is just c. Why is this the case? Just applying the rules again, f dash of x is then c times, and x here, this x is x to the power of 1. Applying the rule 2 for the powers, I get c times 1 times x to the power of 1 minus 1, which is just x to the power of 0, which is 1, so I get c. So this is a very important thing to remember. If f of x is c times x, then the derivative is just c. We can also understand that logically, the graph of f of x equals c times x is a line with a constant gradient c. And we said the derivative is just the gradient of the function.